We're just about ready to introduce some new features of the typing system in C++. That's what we're going to spend most of the week doing. But before we do that, we probably have to remind ourselves how to trace through code and maybe review some things we might be taking for granted. So whenever code tracing comes up in a programming course, I have to explain myself because people always wonder, what's the point of having to trace code? Why not just write code all the time? And the short answer is, well, if we were all perfect at writing code, we'd never have to trace it. We write the code, the computer reads the code, and the code runs. The problem is code isn't always correct. And when code isn't correct, we have to have some way of debugging it. Now, if all goes well, if you've written the code and it's broken, maybe you know enough about how it works. Maybe it works well enough that you can find the bug by trial and error. You could use more organized debugging strategies. There are programs that can help you with debugging. But the problem is we need some fundamental foolproof strategy for understanding what code does. And it's also that we don't always work with our own code. We sometimes work with code that other people wrote, and maybe it doesn't work the way we expect it to. And so we need some way of understanding how it works, and basically the best option in some cases is just to do what the computer does. And that's what tracing the code ultimately is. It's simulating what the computer does with the code. Now, it's also worth considering that one of the biggest issues people have when they write code and have to debug it is that when you've written the code yourself, of course, you're convinced the code is correct. You wrote code, you thought that you knew what you were doing at each step, and then it doesn't work. And you think to yourself, but this should work. I wrote this code, it should work. And as a result, if you allow yourself to make any mental leaps, you might end up skipping over mentally the source of the problem. Only by simulating exactly what the computer does will you catch maybe the minor error that you made, the mistake that you made in your code. And that's one reason having a rigorous tracing strategy can be really helpful, is that it helps you bypass the parts of your brain that want to tell you that, no, this code has to be correct. I'm sure this code works. And I have to do that sometimes. It's true that certainly whenever I can, I avoid having to break the code down into a full trace. But there are times I have to do that. And certainly there are times when even a misconception like the one I'm going to talk about here is the actual source of my problem. And only by tracing it through in full do I actually catch it. And it's certainly really annoying to realize I spent 20 minutes tracing code only to discover a minor error like not realizing how division works was the source of my problem. But it's still a relief to solve the problem, and certainly better to spend 20 minutes tediously tracing through it than to spend 5 hours staring at it and tearing my hair out. And so that's one reason why not only is tracing code a good way to verify that you know how the topics covered by the course actually work, it is also a useful skill to have, not only to be able to write, but to read code. Now, that said, before we talk about tracing these brand new features we're going to discuss this week, let's remind ourselves how fun and tedious tracing actually is. Let's try tracing through this brief bit of code here. Those of you that know me know that I have a specific way I like tracing code. You are not required in this course to trace your code the way I do. You're only required to get the right answer. So that is to say, if you're asked, for example, what is the output of this program? If you can produce the output of the program on paper, then good. You've solved the question, you get the marks. I don't care whether you do it my way or somebody else's way or a way you've made up yourself. As long as you can reliably execute the code by hand and come up with its output, then you have satisfied the requirements of the question. But I have a way that I trace code, and I have over the years developed a very rigorous approach to this, because not only do I have to trace a lot of code, I often have to do it in front of an audience. And I've learned that making a mistake in front of 200 people can be a bit of a tough one. So I have developed a strategy partially based on this idea that I'd rather not make a mistake in front of an audience. And I found it's quite helpful because it helps me not make mistakes when I'm not in front of an audience as well. So I want to trace through main here. And just like if I were tracing a C program, I would first draw a big box to refer to the scope of main. And we'll see, I'll do a few more examples in the next few videos to maybe revisit the tracing strategy that I tend to use with these what I call scoping boxes. Okay, and so then on line number 9, I create a new variable of type int. There it is. So I'll draw its name is x, its type is int, and its initial value is 6. And then on the next line, on line number 10, I create a new variable called y. There it is. Its value is 10. All right, what I want to talk about in this video are the laws of assignment statements. A language like C or C++ owes a lot to assignment statements. Now, it's outside the scope of this course, but there is a broader sort of philosophical point of view that, in a sense, the assignment statement is the defining feature of the class of languages to which C and C++ belong, so-called imperative languages. And that's a very interesting point to look back on in a couple of years if you've learned a couple of other more exotic programming languages and realized that there are languages out there that do not have assignment statements at all. So assignment statements are a big deal. And it turns out that there are some nice rules we can learn about assignment statements that can really help us when we're tracing code, that can help us avoid certain misconceptions. So one misconception, one that I think you're probably used to from CSC 111, is the misconception that just because a variable has type float, that it necessarily, when you use it later, will contain what logically makes sense to a human. So for example, x is 6 and y is 10. Well, we know that 6 divided by 10 is 0.6. And hey, z is a float, so we might expect z is allowed to store 0.6. So does z contain 0.6 when the program runs? Now, unlike most tracing examples, I will actually run this and we'll take a look and see if that can motivate talking more about tracing and the laws of assignment statements. And we can see that z is 0. So somehow z doesn't have the result that we want. And it turns out that the reason for that is what I call the first law of assignment statements. The first law of assignment statements is a good thing to keep in mind, both to avoid misconceptions like this, but it also, as it turns out, really helps us get around certain really complicated assignment statements. It helps us break them down step by step. So what is the first law of assignment statements? I'm going to get us to the end of line 15 first. So on line 15, we create a new variable. Its name is going to be z, and its type is going to be float. There we go. Okay, so we've got on line 16, I'm going to draw it all the way out, this assignment statement here. Z equals x divided by y. The first law of assignment statements says that when you evaluate an assignment statement, you always evaluate the right-hand side first up until you have a final number, and only then do you even look at the left-hand side. So you consider nothing about the left-hand side, what's to the left of the equal sign, until you have a final value. In this case, it's going to be a number, but I guess it could be whatever the type of the right-hand side is. Until you have a final value on the right-hand side, you don't even consider the left-hand side. So let's do that. Okay, so as of this point in the code, so as of the beginning of line 16, the value of z is 0 at the moment. The value of x is 6, and x is an int. The value of y is 10, and y is also an int. And we know that int divided by int equals int. Now, it's true that we might want to store this in a float later, but int over int equals int. And so that means that the result of the entire expression will be an int, and that means, well, 6 over 10. Okay, so 6 over 10 is less than 1. And we know that an int can't store 0.6, so it turns out this value is 0. And that means that as of the end of line 16, the value in z is just going to be still 0. When I actually end up doing the assignment, I'm assigning 0, the int 0 to z. It turns out that what I'm assigning it to is z, a float, which could contain the value 0.6, but by the time I get to z, it's too late. I've already evaluated x over y, and it's already an int. And so I just assign the value 0. And that's why when I go to print out the value of z on line 20, I print out the value 0. The first law of assignment statements. Always do the right-hand side first. Completely ignore the left-hand side until you have the right-hand side done. And to be clear, what I usually recommend to people is when you see an assignment statement when you're tracing, just cover up the left-hand side. Don't even let it influence you. Just ignore it completely, cross it off until you have the right-hand side done, and then uncover the left-hand side and see what you're doing with that final value. So that's the first law of assignment statements. And that's the biggest, most important law of assignment statements as far as C code goes. This is a big deal because we've seen from, if you've taken a course in C, that assignment statements are a big deal in C because C is a pretty small language. There's not that much else going on. And so we have to spend a lot of time filtering through complicated assignment statements. Now, in C++, there are other things we worry about. And in fact, there is this, what I'm going to call the second law of assignment statements, which still applies in C. This is still something we're inheriting from C. But you'll notice I've had to phrase it in a strange, maybe legalistic way. And it turns out that we'll see in a few weeks, maybe 6 or 7 weeks from now, that there are some words in this sentence that are sort of loaded terms. In particular, what does the word copy mean in C++? Strangely, it means something very complicated. And we'll see later that because types are so important in C++, what it means to copy a particular value is actually a bit of a nuanced question. And so I'm going to state the second law of assignment statements with legalese. I'm also going to, this phrasing in brackets here is something we're going to unpack a little bit later this week. But the second law of assignment statements says that whenever I use the assignment operator, that is to say, the single equals sign, whenever I use that, I am always doing a copy. That's it. Ultimately, that's what the second law is stating. I have to use legalese for that because there are times that I use the equal sign, which doesn't really correspond to a copy because it might be an initialization. So for example, if I write a C-style initialization like this, it actually turns out this will be a copy. I'll take a copy of the value 6 and store it in my new variable x. There are certain C-style initializations of a sort that we're going to see later this week. Maybe something that looks like this, where I have an ampersand showing up on the left-hand side, where I'm not performing a copy. And that's why the second law is stated the way it is. But let's try tracing through this code. Okay, so again, I draw a scoping box for main. There it is. And on lines 9, 10, and 11, I make 3 variables. They are named x, which is an int, and it's 6, y, which is also an int, and its initial value is 10, and then z, which is an int, and its initial value is 0. Now, the second law of assignment statements is something we spend a lot of time on in CSC 111, but it's strange how the introduction of all the strange exotic types that we're going to see in this course leads a lot of people apparently to forget the second law of assignment statements. So line 16 says z equals x. Okay, well, obviously following the first law of assignment statements, let's work out the right-hand side. The right-hand side is the value 6. Okay, so I then take the value 6 and I assign it to z. There I go. Okay. Line 17, set x to 100. Okay, so I set x to 100. And predictably, when I print all 3 of these values out, I should print out 100, then 10, and then 6. So we'll take a look to verify that that does indeed happen. And I hope that when you look at this example, there are no surprises. This should be second nature. It should seem almost as if there's nothing that could be in dispute here. And sure enough, x is 100, y is 10, z is 6. So wait a minute, what's the alternative? Like, what misconception can people make here? So one strange misconception that people often make, and I think this is a result of maybe underthinking something. I don't think it's because they don't know this. I think it's because they're letting themselves skip too many steps in their head. I'll get rid of my diagram. They see that the assignment statement z equals x, and then I change x. And something short circuits, and they think, oh, z was set to x, then x was set to 100. So both z and x will now be equal to 100. Because when I say z equals x, I'm saying z always equals x, which of course is not true. All I'm doing is copying the value from x into z. So if x is currently equal to 6, then z will end up being equal to 6. If I change x later, then z stays whatever it was before, because unless I assign something to z again, the value of z won't change after line 16. So the second law of assignment statements is almost second nature coming out of a C course, because we work with so many assignment statements, we should know this by now. But it's strange how in a C++ context, given how many complicated types of things that we're throwing around, people seem to forget this sometimes. So let's see a couple of other examples of the second law of assignment statements. And in particular, I've noticed the second law of assignment statements sometimes falls apart for people when we begin working with more complicated types than just int or float. So here, I'm working with 2 vectors. I'm actually not going to diagram this out fully. I could do this. I could draw scoping boxes and things. What I want to just illustrate, though, is that the second law of assignment statements still applies. Whenever I use an equal sign, I am performing a copy operation. So in particular, if I use an equal sign in a statement that isn't declaring any variables, like these 3, this is always a copy. It's every assignment is a copy. So this would be making a copy of something. So with this. And it turns out that a lot of equal signs you see in C-style initializers are also copies. But we don't yet have enough context to properly explain when copies are occurring in initialization assignment statements. But for now, whenever you see an equal sign where I'm not declaring any variables, you are always performing a copy. So what's happening here? So I'll just sketch out the values of my two vectors. So at the beginning of the program, v is the sequence 6, 10, and 17. And I have a second independent vector called w, which is empty. On line 22, I say w equals v. What I'm saying is, make a copy of v and store that into w. Set w to be a copy of the elements of v. So now w is going to equal 6, 10, and 17. v.at0 equals 999. Okay, we'll draw in some indices here. So v.at0 would be this element here. And notice that by having this sketched out, it's pretty obvious when I modify this, I'm not modifying w. W happens to contain the same elements of v at the beginning of line 23, but it's not the same vector. It's just a copy. And then line 24, push the element negative 116 into the end of w. And notice that, of course, v and w are two completely separate things. They are independent. Just because I copy one into the other doesn't mean that they are forever inextricably bound. So we'll try running this. And I hope, again, once you've seen it, especially once you've seen me sketch it out, that you agree that the second law of assignment statements is still hopefully second nature. But be careful, because if you don't sketch out your answer as you go through it, you might be tempted to think that when I write w equals v, that I'm somehow making w and v the same thing. And one complicating factor is that we're going to see a feature of the language later this week which does allow the same thing to have two different names. So this is making a copy, but we'll see quite shortly that there are ways of having two vectors or two names that refer to this single vector. All right, so I have a function print vector that I've added up here, which just takes a vector and prints out all of its elements. You will notice, I didn't notice until literally right now, we're using a feature we haven't learned yet, so we'll just scroll back down. You'll learn about that feature in about, 2 videos. And then I just print out the values of v and w, and we can see there's the value of v, so it's what we expect from the sketch, and then there's the value of w. Okay, so one other use of that second law of assignment statements, a corollary to that, so not really the second law itself, but something we should observe. This is true in C as well, but it's much less of a big deal in C because the meaning of the word copy is so much simpler in the C language than it is in C++. So what I have here is, again, my print vector function, again with that feature I wasn't supposed to use yet. And then I've got another function called f that also takes a vector as its argument. And I'm not even going to draw this out at all. I just want to make this point. I want to park this here for now so that the material for the rest of the week doesn't need to keep recapping this point. What I'm doing is I'm creating a vector called v in main, which is with 3 elements. I'm then passing that vector into the function f. The function f receives the vector by value. Now it's weird that I have to write by value because we might recall from C that if I use in the C language, everything is always passed by value. So weird that I have to write passed by value in C++. We're about to see why I have to write that in one of the next few videos. If I pass anything by value, and for our sake today, what that means is if the argument is accepted by the function without any ampersands showing up, so you might see shortly functions which take arguments that have an ampersand in their name. If I do not have an ampersand showing up in the name of in the type of the argument anywhere, then the argument is being passed by value. That is to say, the argument that f accepts, this variable called the vector, is an independent thing to what main is passing in. And I'll do another video in a minute going over the process of tracing through code involving function calls. And so you can review that using that other video if you need to. But basically what this is saying is when you pass an argument in by value, You are passing a copy, but to be clear, you are passing it as if it had been assigned with an assignment statement. So it's not just a copy, it's the same kind of copy you would make with an assignment statement. And so it's as if when I pass in the value of v as the argument to f, I have written vector of int, the vector equals, and then passed in this thing here. So it behaves just as if I had assigned that when I start the function. And of course that means this variable here will now contain a copy of the thing that was passed in. If I modify this variable, I'm only modifying my own copy. So we can see inside of f, I set the first two elements of the vector to be 0. And then I print out the vector. And I should expect, because what I passed in was a copy, that those modifications are not reflected when I get back to main. So on line 33, when I print out v, I should see all three original elements. The modifications performed inside the function should not be reflected because the function had a copy and not my original. So we'll run that to verify that. And we can see inside of f, I've set those first two elements to 0, but back in main, the elements are what they were originally because f only received a copy. Okay, so this is all review. All of this stuff is the same. These are the same laws that applied in the C language. One key thing to understand is one advantage of learning C, I guess, was that there are a small set of rather odd cryptic rules, but they're very consistent. Those same rules exist in C++, and they're still consistent. The first and second law of assignment statements, those governing laws that you used in CSC 111 to trace code, still apply now. And we need to keep that in mind because the features we're about to see might make us start to think that those laws can be bent, but they can't.